Welcome, everyone. It is a beautiful fall morning here on the campus of Bluefield State University. I'm Dr. Morgan Sears. I'm the director and assistant professor of mining engineering technology here. And today we're going to be talking about surface mine drilling and blasting. So some surface blasting fundamentals, some words that you're going to hear consistently throughout this presentation. You're going to hear burden. So that's like the spacing between rows of holes. The spacing is the spacing between holes themselves. You'll hear about stemming and subdrilling, and we'll figure out how these influence blast performance. Okay. So the parameters of a blasting round. This lovely drawing from Dyno Noble in 1997 gives us a lot of information about what some of those terms mean. Okay, so we have the bench height here, and the floor or final grade, or the pit floor, right? We have the toe of the slope and the bank angle. As far as drilling goes, here's the crest of the slope, and the spacing to the first row is the top hole burden. And then you have apparent burden and apparent spacing. That the true burden and spacing may be different than the apparent burden and spacing due to the delay pattern. Okay, it's possible. And then you have the back brake, right? So typically, if you want a nice clean high wall, you'll pre-split those. You'll fire the back row first and then delay the rest, so that you can have all that material in place to provide a nice brake line for your next high wall. Okay. Here we also have stem height, so stemming in the hole, which would provide confinement. We'll see a better image of a single drill hole here in a bit that shows some of the other parameters. Okay. So drilling. So that's the first thing you have to do is drill a hole in the ground, right? And there's two types. There's percussion and rotary. Rotary drilling is the most widely used, particularly in coal, in those types of rocks. Percussion drilling is typically used for harder rocks. And it's basically just like using a large jackhammer, right? It just chisels away, and then you pull out the cuttings with cutting fluid. With rotary drilling, though, you either use one of two types of bits, either a drag bit, which has cutting edges on it. It's basically the same as a large dust hog bit for a roof boulder, right? Except you're using cutting fluid here as well to remove the material. They also have the disc cutter bits as well that you can use. That's most commonly what I've seen. And typically drill holes are are either 9 or 12 inches. But they can range from 4 to 15 or 16. Okay, so that's drilling. Then we're going to move into blasting. This image is BHP's claim to the largest single surface blast at a mine here, and it does look really huge. I'm not going to lie there, but anywho, let's get into some of the math involved in designing these blasts. So our first equation, load density, no pun intended. The load density is defined as the diameter of the hole squared times the specific gravity, or the density, multiplied by 0.3405, a constant. Okay. The book does use the word density for this. However, the nomogram on the following page shows specific gravity. So you can use this nomogram on the left for determining your load density based on the specific gravity. The loading density itself is in the middle there. And then charge diameter, right? So if you know the charge diameter and the specific gravity, you can just draw a line and get your loading density in pounds per foot. You can do the same also for detonation pressures, which will generally range between 5 and 150 kilobars, but you'll need to know your specific gravity once again and the detonation velocity with that, which can be calculated. So you can calculate the detonation velocity and then get the detonation pressure. Ground vibration. Ground vibration is also important. I remember when I was growing up, and even when I worked at that mine, it was a very large mountaintop removal mine. We also had contour strips as well, and highwall miner as well. But I remember it was pretty much every evening when they'd set off a shot, and it'd be a pretty big cast blast, and it would rattle the windows in the house. I remember that a lot. But anyways, your ground vibration. So the distance, to calculate the distance to protected structures, you need to know the scaled distance, and then the square root of the weight of explosives per 8 millisecond delay. So we need to know all of those. Here are the federal standards for blast vibrations. You have the blast frequency, and then of course the maximum allowable particle velocity. So as your blasting vibration increases, the maximum allowable particle velocity also allows for an increase. So here's a bench cross section, and it's showing D sub E, B, H, J, T, and L. Okay, so D sub E is the diameter of the hole, or the diameter of the explosive charge. B is the burden. H is the height, and you can see J is the subdrilling, right? So they've actually drilled beneath the floor. This subdrilling is important in quarrying, but not typically used in coal. In fact, in coal, what we usually do is we'll drill to the seam, and then also add 3 to 5 feet of stemming material to pull that charge up off the coal. That way you don't break the coal and lose it when you're loading out the rock. Moving on, here's some generalized blasting patterns. They also show B, the burden, S, the spacing, and then little b and little s. These show expanding V's in a box cut, corner cuts in echelons, a 90-degree corner block, and then also 2 single row shots. So these are just generalized blasting patterns, okay? And so the definition of those blasting variables is here. Like I said, you've got the diameter explosives in the hole, the burden, the spacing, the length of the hole, or H, the height. J is the subdrilling length. T, the portion of the hole does not contain an explosive, or the collar length. So that's at the top of the hole. Like I said, typically you put some stemming material in there to provide confinement. L is the bench height. B is the spacing between, little b is the spacing between rows of holes measured perpendicular to the face. And little s is separation between adjacent holes in a given row. So that brings us to a bunch of ratios, which are equation 10.3 through 10.7. And it shows you that these ratios, B, S, H, J, and T, can be calculated as K sub B, S, H, J, and T multiplied by either the diameter of the hole or the burden. Okay, and so K sub B is the burden ratio, K sub S is the spacing ratio, K sub H is the hole length ratio, K sub J is the subdrilling ratio, and K sub T is the collar distance ratio. Some values of K sub B that would be suitable for limestone and dolomite range from 25 to 35. Reading this, 25 is kind of low for low density explosive like ANFO, and given that ANFO is widely used in blasting limestone, values of K sub B for coal measure rocks would probably be in the vicinity. But actual values are related to the density of the rock. Spacing is determined based on the relationships to the height to burden ratio. Okay, so H to B. For equations 10.8 and 10.9. For burdens, for heights that are between 2 times the burden and 4 times the burden, you'll use the equation S is equal to burden times height, B sub 8, B times H, and take the square root of that, right? So the 0.5 power is the square root. For burdens greater, or for heights greater than 4 times the burden, you'll use S equals 2 times the burden. For equation 10.10, values of K sub S can be 1.8 to 2 if you don't have delays in the row, and 1 to 1.2 if there are delays in the row. So here we have the spacing is K sub S times little b, which also equals K sub S times 1.4 times the burden. And then here we have a final worksheet for blasting rounds, where you can calculate the burden, the spacing for staggered or square patterns. So if you have a sequence firing or simultaneous, you can calculate the spacing, age, K sub J, T, B, and it also gives you sort of like average values for some of these variables here. So other than that, we've got these other ratios, constants, rules of thumbs. Hole length, is generally based on KH ratios of 1.5 to 4. 2 plus 6 is, pretty average. The depth should always be greater than equal to the burden to reduce overbreak. You can have high values of 4, but may cause underbreak or bootlegging. Subdrilling length, so this is only applicable to quarries, not coal mines. It's generally indicated by K sub J values greater than 0.2, and 0.3 is suggested as preferable to ensure a full face in quarry floor. In the case of overburden drilling, however, you have to take care should be taken to limit fracturing the coal seam, right? So that's why you don't want to do subdrilling in coal, right? You stop the coal, you backfill 3 to 5 feet, right? So that way you're not breaking the coal, you're not getting it diluted into the overburden you're removing. You want to keep it intact. And then collar distance can be calculated using K sub T values of 0.7. The uncharged portion of the hull is filled with stemming materials. So it prevents air bias and promotes confinement. So, but wait, how many drills do you need? Well, here's the equations for that, 10.11 through 10.15. And I want to define all of these variables in the next page because it's wild. And so you have a lot of different variables here, and a lot of these are production related, right? So how much bench do you need to expose? How many cubic yards are you removing per month? What's your drill hole spacing, burden spacing, drilling pattern in square feet? Length of drilling in feet per month, Like you need to know how much you're going to have to drill. Number of drill holes, drilling rate, hours scheduled per shift and shifts per days, and drilling days per week. All this is about availability of the equipment, the employees, and all that. So that's the drilling variables. And once you have that down, you're going to ask me, but wait, Dr. Sears, how much explosives do I need? And for that, you're going to need to determine the powder factor. And to determine that, you use equation 10.16, where the powder factor equals 27 times W divided by B times S times H, which is pounds of explosive per hole, the burden in feet, the spacing in feet, and the bench height. This one's pretty important. As far as all these equations, I know there's a ton in here. This one's a pretty important one. And we're going to be working out problems both on the quiz and the exam. Calculating the burden, calculating the spacing, the bench height, and that sort of thing, and then eventually calculating the powder factor. And with that, I'm going to close out this presentation on drilling and blasting. Next time we're going to be talking about some of the methods for equipment selection and that sort of thing. So tune back in, and we'll get into that next week.